lines here. One is the switch, okay, usually a MOSFET, and also an averaging circuit, which will include an inductor. Alright, if you recall your basic resistor inductor series circuit, okay, remember there's a voltage, power supply, DC power supply, inductor and resistor in series, and there's a switch. Okay, you can write the voltage equation like this: VDC is equals to VR plus VL, which is the sum of voltages. By Kirchhoff's law is equals to VR is your resistor, which is IR, right? And VL, the voltage for inductor, is L dI over dt. Okay, when the value of resistor is very small, you can ignore the IR term, and hence you end up with this alone for the inductor. Okay, hence we can approximate the voltage across the inductor to be a constant, and therefore the switch through the current through the inductor will rise linearly when the switch is closed. Okay, just to recall, we went through this before, right? When you have current in the inductor with a switch, what will happen is that when the switch is open, okay, there's a sudden drop in current which is resisted by the inductor magnetic field. Because if di over dt, if the current drops instantaneously, your dt is 0. So di over dt will tend towards infinity. That will result in a voltage spike. Right? Okay? So, in order to prevent this from happening, in your circuit you need to have a return path by adding a diode across the inductor. Okay? When you have such a diode, what will happen is that you will see an inductor current falls slowly, but for the inductor voltage, it drops to -1 volt, because you need to consider the diode voltage drop. Alright, the sign is negative because it's in the opposite direction. Okay? Alright, if we know inductor, the energy stored in the inductor is half Li squared. Alright, when the current through the inductor is increasing, you have additional energy being stored in the magnetic field. If the current through the inductor is decreasing, then this energy is actually being removed from the magnetic field. Okay? So this is how you understand the operation of the inductor in the circuit with a switch. Alright, so if you understand this, let's look at the step-down converter, the buck converter. Okay, how does it work? Alright, this is the arrangement, the circuit arrangement for a step-down converter. You have a DC voltage here, input voltage, there's a switch. Okay, you have a diode connected in parallel with the input supply. Okay, there's an inductor, a capacitor, and a resistor. Alright, so when the switch is first closed, what will happen? The current will start to flow through the inductor and into the capacitor. Alright, at the same time also powering up the load. Okay, so the voltage across the inductor VL, right, is the difference between the input voltage and the output voltage. So VL is equals to V in minus V out. Okay, the diode is reverse bias. Why? Can current flow in this direction? No, right? So you need to know that the diode is reverse bias and does not conduct any current, right? So the rate of change of current to the capacitor is also limited by the inductor, and at some point here the switch is open and the current through the inductor at that time has already risen to Imax, and the energy in the inductor is already stored in the magnetic field. So the moment the switch is closed, what happens is that the inductor will charge up. Okay? What happens when the switch is open? Okay, as soon as the switch is open, the potential on the switch side of the inductor goes to negative. So this goes negative. Okay? But the current continues to flow as the energy in the magnetic field tries to maintain the current. So what happens is that the inductor will discharge in this manner. Alright, thereby completing the circuit and enabling the current to flow into the capacitor. Okay, as the energy in the inductor falls, the current diminishes, means it drops, but the capacitor continues to be charged, but more slowly. Okay, if you ignore this voltage drop, this is what we're going to do for this lecture on switch mode power supply. For all three converters, we will ignore the voltage drop across the diode. We will just assume that there's no voltage drop. Okay, so if you do that, the voltage across the inductor is now negative for V out. Okay, the switching frequency, supply voltage, and inductor value are all chosen such that there is always current flowing in the inductor. Alright, so you have to choose components. You need to rate them so that no matter what happens, with a certain frequency in the switching, there will always be current flowing in the inductor. Alright, so this is something that you have to make sure, and this is called continuous mode, meaning there's always continuous current in the inductor. Okay, and all the circuitry necessary to implement this control function is available as an IC chip. Okay, so what are the waveforms that you will see in the buck converter? Alright, the first one, voltage across the switch. So this is a certain waveform for a certain duty cycle. Alright, so the switch is close, open, close, open, close, open, close, open. Alright? So, close, open, close, open, close, right? That's right. So when the switch is open, what happens is that the current through the inductor will, when the switch is open, the current through the inductor will fall or rise? Fall, okay? And when the switch is closed, the current through the inductor will rise to charge the inductor. Alright? Okay? And this is the corresponding current through the switch. And what you get for voltage across the inductor is it fluctuates between V in minus V out and negative of V out. Okay, very straightforward. Alright, and these two diagrams summarizes what we just said earlier on. When the switch is closed, okay, your VL is essentially V in minus V out. Okay, energy in the inductor will increase. When the switch is open, your VL is equals to negative of V out, and energy in the inductor will drop. Okay. Okay, whenever you talk about inductor, there's always a magnetic field. Alright? So let's go through a definition called magnetic flux linkage, big phi. Okay? This is defined as the integral of the inductor voltage. Right? In other words, between each pulse wave modulation period T, there should not be, in steady state operation, a net increase of electric flux. Okay, so throughout the whole period, the integral of the inductor voltage across 1 RPM, PWM period should be 0. Alright? A useful physical interpretation of this is that the energy stored in the magnetic field will return to the same value for each pulse wave modulation. Okay, if that is true, let's say we were to look at the voltage waveform now. Okay, remember we're just saying that the voltage will fluctuate from V in minus V out to negative of V out. Alright? So if your flux is equals to 0, okay, your VL fluctuates from V in minus V out for 0 to T on, okay, to minus V out from T on to big T. Alright, so you put in